Welcome to this session on understanding outcome data. This is a foundational topic for anyone involved or will be involved in research synthesis, meta-analysis, systematic reviews. And in the next 40 minutes or so, hopefully just 40 minutes, we'll cover two major types of outcomes, dichotomous outcomes and continuous outcomes. And in the first part of the session, we'll talk about dichotomous outcomes, what they are, how effects are measured, how to collect this type of outcome from the studies included in your review. And then we'll move on to continuous outcomes in the second part of the session. So first, why do we need to understand outcome data? Well, when conducting a review, a critical step is understanding, collecting data from the individual studies included in our review. And each of these studies, so for example, here we have study A, study B, study C, study D. Each of these studies measures outcomes from its individual participants. And our job is to select and calculate a consistent effect measure across these studies. We'll discuss about effect measures in a while, but an effect measure is a statistic, a value that represents the effect of interventions on the participants. And when we select and calculate a consistent effect measure across studies, it allows us to compare apples to apples. It allows us to combine them, leading to an overall pooled effect measure. And this part here, the pooling of effect measure in a meta-analysis, that will be covered in the introduction to meta-analysis section, which I believe will be in July. But for today, our focus is on understanding the different effect measures at the study level effects. So broadly, we encounter two major types of outcomes. The dichotomous outcomes, these are the either-or outcomes. The event happened or did not happen, and they have two categories. For example, alive or dead, healed or not healed, pregnant or not pregnant. On the other hand, continuous outcomes, they can take on a wide range of values along a scale. So for example, height or weight. And we'll talk more about this. So as mentioned in the first part of this session, we'll talk about dichotomous outcomes, and the main reference is Chapter 6 and Chapter 10 of the Cochrane Handbook. So what are dichotomous outcomes? The keyword here is dichotomous, meaning divided into two parts. So for every individual in the study, the outcome falls into one of two possible groups or one of two possibilities or events. And when we talk or when we are dealing about this type of outcome, we naturally want to talk about the chance of being in one of two groups. And we express the chance of the event using risk or odds. In general conversation, we usually use the terms risk or odds pretty much the same way. We use them interchangeably, but formally, while both risk and odds are used to express the chance of being in one of two groups, the chance of an event, they are distinct and they are calculated differently. And this difference is very important when analyzing outcome data. So we'll talk about risk first. Risk is probably the concept more familiar to patients, health clinicians, doctors. This describes the probability with which an event will happen. And the formula is the number of participants with the event of interest over the total number of participants. So it answers the question, out of everyone who could experience the event, how many actually did? So for example, imagine we have a group of 24 people who drank coffee, and our event of interest is developing a headache. And out of 24, 6 developed a headache. So to calculate the risk of a headache in this group of people, we take the number with the event of interest, which is 6, and we divide it by the total number of people who could have gotten a headache. So that is 6 over 24, or 1 over 4, or 0.25. And we usually express our risk as a percentage just to express it out of 100 people. So we multiply 0.25 by 100 and we get 25%. So odds. So odds is a bit different than from risk, and it's sometimes less intuitive. This is probably the concept more familiar to gamblers. And the formula is the number of participants with the event of interest over the number of participants without the event of interest. So it answers a slightly different question. Like for every person who experienced the event, how many did not experience it? So going back to our example, we have 24 people who drank coffee. 6 of them developed a headache. So to calculate the odds of a headache in this group, we take the number of people who developed the event, which is 6, and divide it by the number of people who did not develop the event, which is 18. That is 24 minus 6. So that is 6 over 18, or 1 over 3, or 0.33. And unlike risk, we usually do not express odds as percentage, but as ratio, like this. So it's 1:3. And this means that for every person who developed a headache, there were 3 who did not. And you might be wondering, do risks and odds really differ that much? And to answer this question, let's look at 2 examples from caffeine trials. So for our first example, imagine we have a group of 65 people, and our event of interest is having a headache after caffeine intake, developing a headache after caffeine intake. And out of 65, 5 people developed a headache. When we calculate the risk, we get 5 over 65, which is 0.077. And when we calculate the odds, we get 5 over 60, which is equivalent to 0.083. And here, we notice that the odds and risk are quite close. Now, let's look at another example. And this time, our event of interest is staying awake after caffeine intake. So example, we have 165 people, and out of 165, 130 stayed awake after caffeine intake. So when we calculate the risk in this group of people, we get 130 over 165, which is 0.79. And when we calculate the odds, we get 130 over 35, which is equivalent to 3.71. And here we can see that the risk and odds differed substantially. So the first example is a situation where the event is rare. And for rare events, the risk and odds are close. And we could say that the odds approximates the risk. But for common events, like in the second example, the risk and odds are different, and the odds look much larger than the risk. And I guess the important takeaway here is that while both risk and odds are used to measure the chance of the event, they are not interchangeable, especially when the event is common. And that's why it's important to be clear which one you're using in your review. I hope the previous slides were clear, and we now understand how to calculate the odds and risk in a single group of people. But usually in research, for example, in a clinical trial, we are not just describing the chance of event in a single group of people. What we usually want to do is we want to compare the chances of event between 2 groups. So for example, in a clinical trial, between intervention and control. And we want to determine which of the 2 groups has a better outcome. And the standard way of organizing dichotomous data for comparison is the 2x2 table, like this. And this table is the foundation for calculating the effect measures for dichotomous outcome. So here we have 2 groups, intervention and control, and we are interested in whether an event happened or did not in each group. So cell A here represents the number of events in the intervention, cell C, the number of events in the control, cell B here is the number of people who did not experience the event in the intervention, and D, those who did not experience the event in the control. And we also have the row totals, the total number of people in the intervention and control groups. We also have the column totals, the total number of events, the total number of non-events, and of course, the grand total. And when we are conducting the review, specifically when we are collecting or extracting data from the studies included in our review, for the dichotomous outcome, we try to fill this 2x2 table. And here's the 2x2 table with an example laid out. So imagine we're looking at intervention, caffeine and decaf, and our event of interest is developing a headache after caffeine intake. So here we have 17 and 9 for the events in the intervention and control, and 51 and 55 for no events in the intervention and control. And using this table, we can calculate our effect measures to compare the intervention and the control groups. For dichotomous outcomes, we have 3 main effect measures. We have the risk ratio, the odds ratio, and the risk difference. So the risk ratio and the odds ratio, they are relative measures, they are ratios, while the risk difference is an absolute measure, and it is also known as absolute risk reduction. Just a note that these effect measures, these are study estimates, and so we report them with some measure of uncertainty, usually with a confidence interval, which gives us the range of plausible values for the true effect. I believe the confidence interval will be discussed more in the introduction to meta-analysis section, which will be in July. But if you want more information at this point, you can refer to section 15 of the Cochrane Handbook. So first is the risk ratio. So the risk ratio is the risk of events in the intervention over the risk of event in the control group. And going back to our example, the risk of event with intervention is 17/68. The risk of event with control is 9/64. And the risk ratio is just the ratio between these two. So when we feed this into our formula, we get 17/68 is 0.25, 9/64 is 0.14, and we get a risk ratio of 1.79. And in terms of interpretation, since we are talking about a ratio of 2 numbers, that the value of null effects or the value of no effect is 1. So a risk ratio of 1 means that there's no difference between the groups. And the risk ratio of greater than 1 means an increased or higher risk in the intervention group. So for our example, we got an RR of 1.79, and that means that the intervention, caffeine, increased the risk of headache by 79% relative to the control. And we got this 79% by subtracting the null value from the risk ratio of 1.79. So that's 0.79, and we multiply it by 100. And there are other ways of expressing risk ratio in words. So for example, here we can say the risk of having a headache in the intervention group was 179% of the risk in the control group. And I guess it's more a matter of preference. And for me, personally, I like the first interpretation more since it's easier to understand for me. It focuses more on the change, increase, decrease relative to the control group, whereas the second interpretation is more of a direct statement of the ratio. And the risk ratio of less than 1 means a decreased or lower risk in the intervention group. So hypothetically, if we obtained a risk ratio of 0.79, which is less than 1, it means that caffeine reduced the risk of headache by 21%. And this time we subtract the risk ratio from the null value of 1 and multiply it by 100 to get the reduction relative to control. And again, we can express it differently. We can say the risk of having a headache with treatment was 79% of the risk in the control group. So next is odds ratio. And the formula here looks a bit similar to the risk ratio, but instead of dividing risk by the risk, we divide the odds of event in the intervention by the odds of event in the control group. And going back to our example, the odds of event with intervention is headache versus no headache. So that's 17/51. For the control group, it's 9/55. And the odds ratio is the ratio between these two numbers. Again, if we feed this into the formula, we get 17/51, which is 0.33. And then for the control, we get 0.16, which gives us an odds ratio of 2.06. And in terms of interpretation, the odds ratio interpretation is very similar to the risk ratio interpretation. Our value of no effect is also 1, and an odds ratio of 1 means there's no difference between the groups. If it's more than 1, it means an increased odds in the intervention group. So for our example of 2.06, this means that caffeine increased the odds of headache by 106%. We can use the same formula. And again, we can express it differently. We can say the intervention increased the odds of headache to 206% of the odds in the control group. And if the odds ratio is less than 1, it means a decreased odds or lower odds in the intervention group. Hypothetically, if we obtained an odds ratio of 0.06, it means that the intervention reduced the odds of headache by 94%. And we can also express it differently. While risk ratio and odds ratio interpretation, they are very similar. Sorry for saying this again, but this is important. They are not interchangeable, especially for common events. If we misinterpret odds ratio as if they were risk ratio, we risk overestimating or exaggerating the treatment effect we get from our review. And finally, let's look at risk difference. So the risk difference is an absolute measure, and the formula is risk with intervention minus risk with control. Going back to our example, the intervention risk is 17/68. The control risk is 9/64. And when we feed this into our formula, we get 0.25, the intervention risk, minus 0.14, the control risk, which gives us 0.11. In case you're wondering, there's no corresponding odds difference. For risk is a probability. So for risk difference, it's simply a straightforward subtraction of probabilities. But odds, they are a different way of expressing chance of an event. And actually, it's probability over 1 minus probability. So odds, they do not increase or decrease in a straight line like probabilities do. And so we don't get meaningful difference if we subtract odds of one group from another group. Unlike risk ratio and odds ratio, the risk difference interpretation, because it's an absolute measure, the value of null effect is 0. So a risk difference of 0 means that there is no difference between the groups. A risk difference of greater than 0 or a positive risk difference means an increased risk in the intervention group. So for our example, we got 0.11, and this means that the intervention increased the risk of headache by 11 percentage points. And we got this 11 percentage points by multiplying 0.11 by 100, again, just to express the results out of 100 people. And for risk difference, it is particularly helpful to use percentage points, just to emphasize that we are not speaking in relative terms, that it is an absolute measure. This 11% here is not 11% of the control value. This is 11 points higher than the control value. For risk difference, an alternative way of expressing it in words is using natural frequencies. So in our example, we found that the risk with control is 0.14. So we could say that 14 out of 100 people experience a headache in the control group, and 11 more people experience a headache in the intervention group. So we can say it that way. And a risk difference of less than 0 or a negative risk difference means a decreased absolute risk in the intervention group. And here, hypothetically, if we obtained a risk difference of minus 0.11, it means that the intervention reduced the risk of the headache by 11 percentage points. So we basically just flip the signs from positive to negative. Okay, so we have a risk ratio, odds ratio, and risk difference. And how then do we decide which one to use in our review? Well, there are several factors to consider. So first is communication of effects. So first, you have to consider which effect measure is probably easier for your target audience, target readers to understand and use. And for odds ratio, they are less intuitive. They are harder to understand than risk ratio and risk difference, and often misinterpreted as risk ratio. As mentioned earlier, this may be a problem for common events, which may lead to your readers exaggerating the treatment effects. A risk ratio is easier, but as a relative term, it can mean a very big or a very small change depending on the underlying risk. So for example, a 50% reduction in risk can mean a very big change if coming from 80% to 40%. But it can mean a very small change if coming from a baseline risk of 4% to 2%. Risk difference is often the easiest in terms of communication of effect because it is an absolute term. And as shown in the previous slide, we can easily convert this to natural frequencies, to numbers. And also, we can use the risk difference to calculate the numbers needed to treat the NNT. We won't cover this, but the numbers needed to treat it, this is the number of persons who need to receive the treatment or the intervention for one additional person to experience or to avoid a particular event. And we usually don't do this there. We usually don't use this directly in meta-analysis. The second consideration is consistency of effects. So you should consider how consistent is the effect measure likely to be across different studies, across different populations. And there's a study, there's a study of reviews in the Cochrane library. We put the reference here at the bottom. So this study showed that in general, the odds ratio and the risk ratio are more stable. They are less variable across different populations and across different studies compared to risk difference, which can be heavily influenced by different baseline risk in populations. So if you are aiming for a more generalizable effect measure across studies, across populations, then the odds ratio and the risk ratio might be preferred. And the last consideration is mathematical properties. So you also have to consider which effect measure is the most appropriate to use given your event of interest. For risk ratio, the results can be very different depending on how you define the event of interest. So just to explain this further, for example, if you are looking at the good outcome as the event of interest rather than the bad outcome as the event of interest, you might get different risk ratio if you flip the definition of the events. Another example is success versus failure. You might get different risk ratio depending on your choice, which group you would like to focus on. And perhaps a better example is the common dichotomous outcome of dead or alive. So with this outcome, we have two categories. You can look at being dead or mortality as the event of interest, or you could look at being alive, survival, as the event of interest. And depending on that choice, you might get different risk ratio. And I guess what's important here is to be clear early in your protocol with the definition of your event of interest and stick to it consistently. Try to avoid changing the definition of interest while you're doing your review, because obviously it could introduce bias to your review. For odds ratio and the risk difference, it generally doesn't matter which way you define your events of interest, and the effect measure essentially just flips signs. So for risk difference, from positive to negative or vice versa. For odds ratio, from increase to decrease or vice versa. Odds ratio has some mathematical advantages over risk ratio and risk difference. It is unbounded. It can range from 0 all the way up to infinity. And this is mathematically convenient for certain statistical methods. And so some statisticians prefer to work with odds ratio for that reason. Sometimes your Cochrane group may have a preferred effect measure. So please check if there's a policy that you have to follow. So this table provides us a summary, a handy overview of the properties of effect measures for dichotomous outcomes in terms of communication, consistency, and mathematical aspects. So what data do we need to collect to analyze a dichotomous outcome? The 2x2 table is key. So essentially, the 4 numbers shaded here are all we need to collect from the studies. So the number of events in the intervention and control, and the total number of participants in the intervention and control. And when we have these 4 numbers, of course, we can fill the table. And also, if we have these 4 numbers, we can input them into the Cochrane's review production software, the review manager, RevMan, and it will calculate for us the effect measures. It will calculate the risk ratio, the odds ratio, and the risk difference with a measure of uncertainty. When we are collecting dichotomous data from the studies, try to collect the actual number measured for each time point for each outcome at each time point. This is important because some studies would have multiple follow-up periods, and at each follow-up, the number of participants might differ due to loss to follow-up or some other reasons. And this is related to the issue of intention to treat versus per protocol analysis, which I believe will be covered in a later session. But if data is missing, it's important for us to be aware of that and to decide if it's reasonable to use, for example, the sample size at baseline or a different sample size as the denominator in our analysis. And what's important is to be clear with our decisions and to get statistical advice if needed. If a study doesn't give us the ideal 2x2 table, it's okay. Often data is reported in other formats, but there are ways that we can use to still use them in the review. So for example, studies might report percentages of events. And if the sample size is known, then we can compute the number of events to fill our 2x2 table. Some studies, they do not report separate values, statistics for the intervention and control. They just report an overall effect estimate, like, for example, the risk ratio or the odds ratio. And we can still use this as long as they've been reported with a measure of variance, like the standard error and the 95% confidence interval. And we can still include these estimates in meta-analysis using generic inverse variance method, which will be covered in a later session. Okay, I hope that's clear. We would have time for questions later. So let me check the time. Okay. And now let's switch to continuous outcomes. The main reference is the same, Chapter 6 and Chapter 10 of the Cochrane Handbook. So what are continuous outcomes? Unlike dichotomous outcomes with just 2 categories, continuous outcomes can take a wide range of values along a scale. So for example, height or weight. So a person could be 180.5 centimeters tall and can weigh 70.3 kilograms. So the values can, in theory, fall anywhere within the range, not just whole numbers. An important characteristic of continuous outcomes is that the intervals between values are equally spaced and have the same quantitative value. So for example, the distance between 1 and 2 centimeters is the same as the distance between, let's say, 173 and 174 centimeters. Many of the scales that we use in research don't formally meet this definition. So for example, some scales, they can only take in whole numbers, and also some scales, for example, quality of life scales, depression scales, pain scales. So for these scales, we really can't say if the distance between 1 and 2 points is quantitatively the same as the distance between 29 and 30 points. And the outcomes that we collect from this type of scales, technically, they are not truly continuous, more of ordinal, but in our analysis, we often treat them as if they are continuous. And I leave it at that for now. It's just a note. I believe that there'll be a separate session covering this type of outcomes. So to summarize continuous outcomes in a group of people, so for example, here in our table, we have the caffeine group and their irritability score. we have the decaf group and their irritability score. So to summarize continuous outcomes, we typically use two key parameters, the mean value or the average score, and the standard deviation or the SD, which is the measure of spread or variability of the data around the mean. So it shows us how much individual values differ from the average. And just to illustrate why it's important for us to also include the standard deviation when summarizing continuous data. For example, here we have a group of participants and their individual scores represented by the blue diamond on a continuous scale ranging from 0 to 20. The average score in this group is 10 with a standard deviation of 1. And here we can see that the individual values are more or less close to the mean. Now, in this case, we have the same number of participants, the same mean of 10, but a higher standard deviation of 3. And we can see here that the individual values are scattered either side. So the data is showing higher variability. And here, even more spread. So we have standard deviation of 5. So the data is more scattered either side. So we can see that with the same number of participants, with the same mean, without the standard deviation, we miss some important information about our data. And the standard deviation is essential in understanding the distribution of continuous data in a group. So similar to dichotomous outcomes, we also have effect measures for continuous outcomes. The two main effect measures are the mean difference and the standardized mean difference. And again, these effect measures are study estimates. So we report them with measure of uncertainty, usually with a confidence interval. So the mean difference is used when all studies use the same measurement scale. And the formula is mean of intervention minus mean of control. And it looks similar to the risk difference formula. So for example, here in our table, we have the mean irritability score of the caffeine group. We have the mean irritability score of the decaf group. So the mean difference is simply 20 minus 33, which is equivalent to minus 13. And in terms of interpretation, mean difference is also an absolute value. So the value of null effect is 0. So a mean difference of 0 means no difference in the average score between the groups. A mean difference of less than 0 or a negative mean difference means that the intervention group mean is lower. So for our example, we got a mean difference of minus 13. This means that on average, the participants with the intervention scored 13 points lower on the irritability scale. And a mean difference of greater than 0 means that the intervention group mean is higher. So hypothetically, if we obtained a mean difference of 13, it means that the intervention scored 13 points higher on the irritability scale. But interpreting mean difference requires context. We know that, that a mean difference of minus 13 indicates that the intervention scored lower on the irritability scale. But what does that really mean? Is it a beneficial effect? Is it a harmful effect? And to answer that question, we have to have knowledge of the scale that we're using. First, we need to know the direction of the scale. Does a higher score mean more irritability or less irritability? In this case, let's assume that in the scale, let's assume that the higher score means more irritable, which means that a score of minus 13, that means that the intervention group were less irritable after the intervention. We also have to know the length of the scale. How large is 13 points relative to the length of the scale? Is it a 0 to 20 point scale? Is it a 0 to 100 point scale? Let's assume that for this scale, it's 0 to 50. We also have to know what's the minimally important difference. This is also called clinically important difference. Here, let's assume that the minimally important difference is 5. And since what we obtained 13 which is larger than 5, then we can say that that the intervention caused a clinically relevant reduction in irritability. And lastly, we also have to consider whether it's a good or bad outcome. We've established that a higher score means more irritable, and more irritable is a bad outcome. So that's how we usually interpret the mean difference. And it's important for us to include this information about the scale in our protocol, in our review manuscripts, just so the readers could also understand the conclusions of our study. Now, what if the studies included in our review use different scales to measure the same underlying concepts? And in general, we encounter two scenarios. In the first scenario, the studies use different units of measurement. So for example, here we have study A reporting in kilograms, B and D reporting in grams, and then study C reporting in pounds. And in this case, it's okay because we know the conversion factor to make the unit of measurement similar. The second scenario is when the studies use different scales to measure the outcome. So for example, here, study A, study C used scale 1, study B used scale 2, study D used scale 3. And just to put this in context, we have many pain scales. So let's think of it as study A, study C using pain scale 1, study 2 using a different pain scale, study D using a different pain scale. And in this case, we can no longer say that the mean differences from these studies are comparable. So for example, a 5-point mean difference using scale 1 is not equivalent to a 5-point mean difference using scale 2 or scale 3. And when different scales were used to measure the same outcome, we use the standardized mean difference. So conceptually, the standardized mean difference, here's the formula. So it standardizes our difference. So if you look at the numerator, that's mean of intervention minus mean of control. That's our mean difference. So it standardizes the difference by dividing it by the pooled standard deviation of both groups. We have the formula for the pooled standard deviation in chapter 6 of the Cochrane handbook. And also, if you're using RevMan, if you input the values, it will calculate the standardized mean difference for us. So what this formula does, it allows us to express the mean difference into a common metric. So now it is in standard deviation units. So we are no longer using the unit of measurement of the original scheme. So it's now in standard deviation units for all the studies. And when we are using standardized mean difference, just be careful that the scales that you are using are truly comparable, because it assumes that the scales measure the same underlying concepts. And it's up to you to use your judgment and decide if the scales are similar enough to be combined to give meaningful answer to your review question. In terms of calculation, as mentioned earlier, the review manager will run this calculation for us. And in terms of interpretation, well, the SMD is less intuitive and it's harder to interpret as compared to the mean difference. So going back to our example earlier, using the same numbers, so the standardized mean difference turns out to be minus 1.5, and we interpret this as irritability was 1.5 standard deviations lower in the intervention group. But yeah, that is not as easy to understand as the mean difference. But in general, the interpretation of the standardized mean difference depends on the same factors as the mean difference. We also have to consider the direction. We also have to consider whether it's a good or bad outcome. And we can also compare the standardized mean difference to available SDs. So we can look at what's typically reported in the studies. But sometimes even with this, with all of these considerations, it's still difficult for readers to interpret the standardized mean difference. And so we convert the results to a specific, more familiar scale for reporting. And just to show an example, so this is from this study, from this resource. could have a look in your own time. So in this meta-analysis, the authors included 2 studies, Carret 2003 and Ryan's 2005, and the overall outcome was pain. In the Carret study, pain was measured using the SPADI scale, the Shoulder Pain and Disability Index Pain Scale. And in the other study, used a different scale, the visual analog scale. So the authors pulled these 2 studies and obtained a meta-analytic standardized mean difference of 0.21 with a 95% confidence interval of minus 0.65 to 1.07. So what the authors did was they converted this standardized mean difference to their choice, to SPADI pain scale. So they multiplied the standardized mean difference and the 95% confidence interval by the pooled baseline SD of the Carret study. And the pooled baseline SD, when they calculated it, it turned out to be 18. So that is 0.21 times 18 minus 0.65 times 18, 1.07 times 18. And then the authors reported both the SMD and the equivalent MD. So they said SMD of 0.21 with a 95% confidence interval, and this is equivalent to a mean difference of 3.78 with the corresponding confidence interval on a 100-point SPADI scale. Just a note that the accuracy of this back transformation from SMD to MD depends a lot on the pooled baseline SD that you will use. And in meta-analysis, some studies would have high variability at baseline, low variability at baseline, and so you might get different results depending on the pooled baseline SD that you will use. And I guess it's important to be transparent of the choice, and of course the decisions that you're making has to be included in the manuscripts. Okay, let me just check the time quickly. Okay, so analysis of continuous data is based on the assumption that the data is normally distributed. So here we have the familiar bell shape. The mean is in the center, also the median because it's normally distributed. And the measurements are spread out evenly to a width of roughly 2 standard deviations. But in some cases, this assumption is violated. And we have what we call skewed data, like the blue density curve here. And a classic example is the length of hospital stay, where most days are short, but few are very long, creating a tail. And it's important for us to know if we have skewed data because the standard analysis, standard meta-analytic techniques that we use are based on the assumption that the data is normally distributed. And so you might you really have to watch out for skewed data, and you might suspect skewness of data. For example, if studies report the median or interquartile range rather than the mean and SD, or sometimes you would see log transformations, or they report the geometric mean. So that gives you some indications that probably the data is not normal. And we sometimes can also see unusually large standard deviation in relation to the mean. And if a study reports both the minimum and the maximum in addition to the mean and SD, then we can use these calculations to check for skewness of data. And if you do encounter skewed data in your review, then again, it means that the standard methods might not be appropriate. So get statistical advice before proceeding. It might be that there's no action required, but possible actions may include sensitivity analysis without the skewed studies, log transformation, or other methods. So what data do we need to analyze a continuous data? So we need 6 numbers. So we need the mean, the SD, and the sample size in the intervention group, and also the mean, SD, and the sample size for the control group. And this applies both for the mean difference and for the standardized mean difference. And again, when you collect data, try to collect the actual number measured for each outcome at each time point for intention to treat considerations. There are different ways continuous outcome data are reported, and you will likely encounter these different ways when you do your review. So for example, studies report the post-intervention scores or the final measurements, just the final measurements, the average score at follow-up for the control group, the average score at follow-up for the intervention group. Some studies report the change from baseline score. So for example, here they calculate baseline to follow-up, and then they report the mean change and the standard deviation of that change for the control group and also for the intervention group. For the post-intervention data, just the final measurements, we can compute the mean difference. So it's simply the difference between these two. But also, for the change from baseline score, we can compute the mean difference. So it's the difference between this change in the intervention group and the change in the control group. Although here, it basically would look like a difference in differences. And the key question is, can you combine studies using post-intervention versus change from baseline in one meta-analysis? And the answer for mean difference is generally yes, since both post-intervention and change from baseline scores measure the same intervention effect. But for standardized mean difference, the answer is no, since the standard deviation of post-intervention score and the standard deviation of the change from baseline score are different because we take into account the repeated measures over time of individuals for the change from baseline score. So we cannot combine them. Some studies would report ANCOVA, the ANCOVA results, the analysis of covariance results, which adjust for baseline. And this is actually statistically preferred. So we can combine this with other studies using the generic inverse variance method. In practice, we work with what is reported in the studies. We work with what is available. So again, we can use either post-intervention or change scores. We can use a mixture of the two for mean difference, but not for standardized mean difference. Just try to be consistent as possible to report the same measure for the same study and try to make as many studies as similar as possible. And again, try not to be selective between post-intervention and change from baseline score, depending on the results. Sometimes you would be tempted to calculate change scores from the studies, like if they report baseline and follow-up for both groups. But just a note that the calculation of this requires the standard deviation of the change, which is different from the standard deviation in groups. This standard deviation of change requires the correlation of outcomes across time points, and that is often not reported in the studies. So if a study doesn't give us the format that we want, the ideal mean SD format, some studies would give us the standard error, confidence interval, p-value, t-value, median, interquartile range. It's okay. We can often calculate or estimate the mean and SD from this. And of course, we can contact some authors if we need more information. And similar to dichotomous outcomes, some studies do not report the separate mean SDN for intervention and control. Rather, they report an overall effect estimate, like the mean difference, ANCOVA, ratio of means, geometric means. And again, as long as these measures were reported with a measure of uncertainty, like the SE or the 95% confidence interval, we can include them in meta-analysis using generic inverse variance method. So what to include in your protocol? As you plan your review and write your protocol, be sure to specify the effect measure or measures that you would want to use for your outcomes. Will you use risk ratio, odds ratio, risk difference for dichotomous outcomes, and mean difference or standardized mean difference for continuous outcomes? Will you use more than one? Will you prioritize one over the other? And pre-specifying this in the protocol adds rigor to the review process and ensures transparency as well. For continuous outcome data, mention your plans for handling different scales and whether you have a preference to use post-intervention or change scores. You also have to mention your plans for converting statistics to the required formats, and if possible, include the minimally important differences. So just some take-home message for both dichotomous and continuous outcomes. For dichotomous outcomes, again, risk and odds are two ways of expressing the chance of an event. And our main effect measures are the risk ratio, the odds ratio, and the risk difference to compare the chance between two groups. And when using RevMan, what we need to enter is the number of events and the total number in each group. For continuous outcomes, our main effect measures are the mean difference and the standardized mean difference to compare groups. And for basic analysis of continuous data, we need the mean, the SE, and the number of participants in each group. Watch out for skewed data and handle change and post-intervention data appropriately, especially when you are working with standardized mean difference. And again, even if the ideal format is not reported in the study, there are some workarounds that we can use to still use the data and include them in our analysis. So that concludes the presentation. These are the references and the acknowledgements to everyone who contributed to the slides.